How you doing? The last time you were watching me talk, this was the slide we saw, and now that I've got you all charged up to keep going, we're going to move on. This might be a little longer than I intend, but there's going to be a lot of information in here. I also want to point out that it is Tie Tuesday, so I need to be wearing a tie. You might not be watching on Tuesday, but today is Tuesday, March 31st, Tie Tuesday of homeschool. Anyway, we are going to continue with current. Now, there's some information. This is kind of extra information, but really understanding. Current is actually electricity that is going through the circuit. So current are the charge carriers or the electrons that are traveling through the circuit. Again, we call them charge carriers because we're going to use what's called conventional current, as you saw last time. So a current, as you can see here, is technically the number of charges that pass through a part in the wire in the circuit in a given amount of time. We always talk about current in amps, but an ampere or an amp is actually a coulomb per second. So we want to know how much electricity is traveling through a wire every second. So we start thinking about, maybe like two different light bulbs, a really bright light bulb versus a really dim light bulb. You might think to yourself, the bright light bulb has more electricity going through it, and that's probably true. It's got more charges every second going through the light bulb. Now, a note about voltage down here, and we're going to talk about that in a little while. Voltage doesn't actually move. Remember, that voltage or the electromotive force is the thing that makes the charges move. It doesn't actually move itself. So this is just talking about conventional current. Again, we're going to talk about conventional current, which means the electricity or the current is flowing from the positive side of the battery, high potential, to the negative side of the battery, low potential. Now, this is extra information, but this is really for us. DC current and AC current. You've probably heard of AC/DC, the band. Totally different. DC current is a battery. That is direct current. That is electricity that flows in one direction. Your cell phone has a battery, cars have batteries, most things we use. My laptop has a battery. Most things we use in our everyday life that is not plugged into a wall is DC current. Now, AC current means it oscillates. It's alternating current. AC current switches from a positive and negative, goes back and forth, back and forth. Here in the United States, it's 60 times per second, or 60 hertz. Now, there are pros and cons to both of them. AC current can travel much, much further, power a lot of things at once. DC current isn't very good for that. DC current is good for powering small things like laptops and cell phones, etc. Now, everything that plugs into the wall gets the same amount of electricity or voltage from the wall. That same push, 120 volts come out of the wall. So there are elements in the circuit that we're going to talk about, like resistors and capacitors, that help us to use everything, right? Because my cell phone takes a different amount of electricity or a different amount of push, say, than my refrigerator. So those are the things that we explore, AC current and DC current. In our class, we're going to focus specifically on DC current. Now, to understand a circuit, we're going to have this little analogy. This would be like the top of the battery. This would be like the bottom of the battery, or the voltage source. So I have a high potential, the plus side, the low potential, the bottom side, or the negative side. When I hook it up and I make the electricity flow, that current goes into the wires to do whatever I want to do. Like if I had a little light bulb here. Now, granted, water's not powering light bulbs, but this is like the electricity flow. So it's always going to flow from high potential energy, down to the low potential energy. Now this battery, or the voltage pump, is what pumps it back up to give it back that potential energy. Now inside of a battery, there are chemicals, there's a chemical reaction, there are things called anodes and cathodes, you're learning chemistry, that help with that. So here is my analogy for the two. Here is my high potential, right? Here's the flow, the plus side of the battery. Hooked up my light bulb, it does something right in there. So as the kinetic energy is moving, right there, because it says a lot of kinetic energy, that's powering my light bulb. So the voltage pushes into the light bulb, makes those suckers move, does work, until it uses it all and gets down to the bottom of the battery, the low potential energy. It settles down at the bottom. Then the battery has a chemical reaction, pumps it back up. So it happens all over again. Now, this is a circuit. This is what we pretended to build in class at home with the light bulb, battery, and wire, and what you use that little animation for. But we draw them differently. We draw circuits instead of all this stuff like this, where this thing is a battery, these things are wires, and this little guy right there, that's a light bulb. So the next several minutes are going to be just going through all of the circuit elements. Now notice how nice and straight everything is. You draw a circuit as straight as possible, kind of like a box. Even if it doesn't look like that, we draw them as straight as possible. So here are all of our circuit elements, right? These guys are wires. There are two kinds of wires. They're solid and braided. Most of the wires we use are braided because they're cheaper and they're more flexible. But a solid wire also works. They're just metal conductors that are coated on the outside with an insulator. And we draw them literally with just straight lines. That's a wire, that's a wire, this is a wire that turns. Now resistors specifically don't allow electricity to flow as easily. Wires have almost no resistance. Resistors try and hold that back. They come up with resistance. Now a resistor is drawn with this little squiggly line, just like that, kind of like a W, connected to wires. Now I have a light bulb here because a light bulb acts as a resistor. It slows down that flow of electricity, right? So it is literally a little resistor with a circle around it. That circle represents like the light bulb itself. So a resistor and a light bulb. Now resistors are one of those things that help us be able to plug cell phones into the wall because they change how much electricity is flowing. A power supply, like a battery, well, we have big power supplies that like power my apartment. We have small power supplies like batteries. They're all drawn the same way. This technically is a cell. This technically is a battery, more than one cell. Notice how we have two of them. Now a battery is always a very long side and a very short side. The long side is the plus. The short side is the minus. Again, connected to wires. And it doesn't matter if I have the battery this way or I can turn it up, I'm sorry, that way, right? My battery can go, pretend this marker's a battery. I can have that way, or I can put it that way. It doesn't matter. With the plus side and the minus side, the plus side and the minus side. And then the wires are touching the plus and the minus. The reason why I have this is because you can literally make a battery electricity with a zinc nail and a copper penny that acts as a power source. Now this is a capacitor. I'm just going to talk quickly about them. Capacitors are not something we use in our class, but a capacitor stores electricity. If you ever had any of those old cameras with an actual flash, not a cell phone camera, the disposable ones where you press the button, it charges up, goes whee, is it really high sound? Well, the capacitor stores a whole lot of electricity. Then when you take the picture, that flash is a release of electricity, a release of energy really fast. A capacitor, if you ever see one, is two parallel lines very even. Remember, a battery is one long and one short. A capacitor is two of the same size. Now a switch obviously is something that turns the electricity on and off. A switch is just like a little door. This is an open switch. So we would say, a question would be like, hey, if there was draw something with a switch, if you closed the switch, when we close the switch, it looks like a wire. So we always draw them open. And a switch literally lets electricity go on and off. It's a little counterintuitive because an open switch means electricity is not flowing. A diode, this is something, again, we don't talk about in class. The only reason I'm showing it to you, or I should say as freshmen, only reason I'm showing it to you is because you know things about diodes already, like an LED TV is a diode. Your camera phone has a diode for a flash, or an LED. A diode is something that literally only allows electricity to flow in one direction. If any of you know how to program, computer program, you've seen this symbol before because it means the same thing. It means flowing in one direction. So a diode, a battery, it doesn't matter if I hook up the light bulb to the top or the bottom. A diode has to get hooked up in a specific way. Now, almost done with this lecture. I know we're at 9 minutes now. It'll be only another few minutes. Resistance. Resistance is something that controls how much electricity or current is flowing through a circuit. Resistance resists the electricity flowing in the circuit. Now, the resistance of a wire, of an object, depends really on two things. How big, this should say the resistance of the circuit. How big the voltage is, in other words, how much I'm pushing that electricity through the circuit, and how big the resistance is. So that is what controls the current flowing through. A 100-volt battery pushes more electricity than a 10-volt battery. But resistance, like the wires in the circuit, actually do something else. So what is resistance? Resistance is opposition. It's like friction. It slows down that electricity, and it's measured in something that's called ohms. We're going to end today with Ohm's law. And ohm is this fun little symbol, omega. Now, there are factors that affect resistance. Those factors are these three things. Think about it. Long wires, the thickness of a wire, or the temperature. Now, resistance slows down electricity, makes it harder. So a really long wire has a high resistance. The longer the wire, the higher the resistance. Now, wire thickness is something that's called gauge. So now I want you to think about like an analogy. Think about the hallway from my classroom, where we usually are, all the way down to the history wing. If I made that longer, it would take you longer to get there. That'd be resistance. Now the thickness, if I made the hallway really wide, you can run back and forth. It'd be really easy. Electricity can go through thick wires easier than thin wires. So thicker wires, a fat wire, has a low resistance. The thicker wire, smaller resistance. Teeny tiny thin wires, if I brought that hallway in so it was barely bigger than your shoulders, you got to go sideways and wiggle your way through. That would take a long time. That would be a higher resistance. Now the temperature is the one that people confuse. If it is super, super cold outside or inside, often like my classroom, you don't want to move. You just, you don't move very fast. Cold wires have low resistance. Well, why would that be? Because if the molecules inside the wire are not moving around so much, the electricity can get through much, much faster. If I filled that same hallway we were talking about with a bunch of people, and your goal was to get from my room all the way down to the history room, and I made those people run back and forth as fast as they can, back and forth, back and forth, back and forth, back and forth, as fast as they can, it would be harder for you to get through. And when things get warm, molecules move faster. So, to summarize, a long wire has a high resistance, a short wire has a low resistance. A thick wire has a low resistance, a thin wire has a high resistance. A hot wire has a high resistance. A cold wire has a low resistance. So ideal conductors are short, fat, cold. Ideal insulators, long, skinny, hot. The material obviously, the material obviously matters. Conductors versus insulators. Now, last two slides. How do we calculate stuff? This is my favorite part. Ohm's law is something that tells us voltage, current, and resistance. It is a relationship. If I hook something up to a battery and I have a high resistance, electricity goes down, low resistance. This is voltage equals current times resistance. Then, as electricity is going through wires and making things work, we have something that's called power. Now, power we can think of as brightness for a light bulb. The brighter the light bulb, the more power there is. Now, notice power is current times voltage. So these two things are very similar. V equals I times R, and P equals I times V. These are Ohm's laws. Now, Ohm was a scientist, this story may or may not be made up, who was working with electricity and trying to figure out how electricity works. And he electrocuted himself, and he set himself on fire. And he was on fire, and it was hot, and it was terrible, and he didn't know what to do. But his office, his lab was by the ocean or the sea. So he ran out of the lab on fire, hair on fire, ran out of the lab, dives into the ocean or the sea to cool himself off and turn the fire out. And that's when it clicked. This is how you remember these equations. You think about Ohm, you think about the famous song that you've been lied about. The famous song, Twinkle, Twinkle, Little Star. You ready? Twinkle, twinkle, little star. Voltage equals I times R. Splishy, splashy in the sea. Power equals I times V. Now I know my ABCs. They are the same tune as this song sees. Okay, I made that last part up, but this is how you can remember it. If you practice and practice, ready? Gonna do it one more time all together. 1, 2, 3. I don't hear anybody. Try it again. 1, 2, 3. Twinkle, twinkle, little. Good. Splishy, splashy in the sea. Power equals. And now, that's all I have for you today. There will be some practice. These are easy, and then we're going to get into drawing circuits and solving circuits again. So hopefully when we get back to school, we can play with some fun electricity stuff. Keep all the questions coming. This was 16 minutes, but we got to sing. If you want to record yourself singing a song, Middle Table and others, you should record it. You should post it on Classroom or Padlet or somewhere so we can all have fun with it. Everybody should do these. If we ever go back to school, that will be some extra credit. Sing some kind of physics song, relates anything we know to physics. Anyhow, talk to you all soon.